Okay, thank you. Good morning, everyone. I would like to share with you our experience in designing a recommendation inference engine, specifically for OCP. My name is Youn-Long Lin. I am from NEUCHIPS Inc. Recommendation is a very important task in data center, e-commerce, etc. Whenever we use social media, e-commerce, anything on the web, the recommendation will predict whether the user would like to click on a service or product or advertisement, etc. In order to satisfy the quality of service and driving the revenue bottom line, the recommendation has to be very accurate and in real time. But in order to do that, the model getting bigger and bigger. It requires a lot of computation and memory access. So this calls for a domain-specific accelerator solution. Just in yesterday's, during the opening keynote, Meta mentioned that recommendation is one of the most important task role in both training and inference. This chart was brought from OCP Summit 3 years ago on the challenge of deep learning recommendation model. The challenge is quite different from conventional AI such as vision or language task. It includes large memory capacity for storing the sparse feature and dense feature. And because the number of access and the number of inference is very high, so we need very high memory bandwidth. And to do the interaction between the sparse feature, user, and category data, etc., we need communication bandwidth within the chip. Finally, the neural net model requires heavy computation. So how to address all these 4 challenges is important to come up with an efficient solution. In NEUCHIPS, we address these 4 challenges by designing a 7-nanometer chip like this one. For the compute bottleneck, we design about 200 tera operation per second computer engine in 10 separate units. And we also design specifically for interaction between different feature and different user in a terabit per second bandwidth. And for the memory bandwidth, we design cache and different size of on-chip SRAM and different access scheme and load balance for external DRAM access to achieve over 3 terabit per second of lookup bandwidth. And for the memory capacity, we put 4 LPDDR5 channel on the chip. Altogether, we can have 128 gigabytes per module. And we also have huge on-chip SRAM up to 160 megabytes. Yeah. I'm happy to say that we just got a chip back last month, and it's bring up in our lab, operate as design spec. It will be able to deliver 20 million inference per second at only 20 watts. And since the size is getting bigger and bigger, and we also have the technology to promote the so-called floating point 8-bit. It's getting popular in many other applications as well. 32-bit is too expensive, so people try to do 16-bit or 8-bit integer. But recently, we see that 8-bit floating point is getting wider support. And at NEUCHIPS, we have a more flexible floating point 8. So it includes the popular two type of 8-bit, and we also have configurable 8-bit to achieve better efficiency and better accuracy. For example, in this DLRM, if we use 32-bit floating point, we can say the accuracy is 100%. But if we use the BF16, almost no loss at accuracy. But if we go to 8-bit integer, then the accuracy loss may suffer to below what is acceptable. But with our floating point 8 in flexible so-called FFP8, we can achieve almost 99.99% of the original accuracy. So basically using only a quarter of the storage and a quarter of the bandwidth and much less computing energy. Yeah, this is how we will bring up our system. This chip will go into an inference module in dual M.2 format, and then we put into carrier card. And we work with our system partner to build a whole system in Yosemite V3 rack. And just as I said, the chip come out from the fab last month, and then we are very happy to say that it's the first cut work with the system. We are coming out soon. And in addition to hardware, we also have the full stack of software, starting from popular framework like PyTorch and TensorFlow. And it supports not only DLRM, but also other popular recommended model, including wide and deep, deep and close, and newer model. Yeah. And from there, we compile to ONNX intermediate format, and then use our SDK to drive the hardware through PCIe. Okay. Sorry about it. Yeah, sorry about this screen, but the message is that we emphasize on software, hardware co-design in order to enable all the efficiency. So our software support security and programmability and scalability, and it also support dynamic and tuning of multiple car for big model and a single car for multiple model. Yeah. Yeah. In summary, the recommendation is a very important application, and we designed specifically for the efficient recommendation inference. And we understand that the industry is converging on the 8-bit floating point format. And we have a special technology that give the system high accuracy at a low hardware cost. And we believe that hardware-software co-design is required, and it demonstrates that we can deliver high performance through tightly cooperation between hardware and software. Okay. And NEUCHIPS has a very strong support from the semiconductor and the cloud ecosystem of Taiwan. I'm happy to announce that just this week, we closed a funding of $20 million for our further development of this system for the OCP community. We have a booth in the exhibition hall at number C23. You are welcome to visit us for more detailed discussion. Okay. Thank you. I would like to ask you for any question.
Yes, thank you. If anybody has any questions, come up to the 2 mics up front.
Thank you for the nice presentation. I have a quick question about the, just I hear you mention per word, like, can you say that again, how many TOPS per words that you can support?
Yeah, this design is for this chip we run at here. It's a smaller, we had to put into the dual M.2 module. It's 25 watts, the power envelope.
How many TOPS?
How many? 200.
200.
200 TOPS, integer 8.
Got it. And also, like, I'm not sure if I catch, like, what kind of like NOS you using, like is it 7 nanometers or like?
It's a 7 nanometer.
Okay, 7 nanometer.
7 nanometer, yeah.
Got it. Okay. Yeah, I think what's the size dimension?
Approximately 20 by 20. It's a 400 millimeter square.
20 by 20 millimeter.
Millimeter, yeah, 20 millimeter by 20 millimeter.
And the thickness, do you know, right?
Thickness.
Yeah.
We never care about thickness.
Oh,
Sorry
okay.
about that.
All right. Appreciate that. Right. Thanks for information.
Okay, thank you.
On the thickness, it's a M.2 card, which I believe is an 050 thick card.
Oh yeah, yeah. The thickness in the module level is a dual M.2.
Right.
Dual M.2, yeah. I thought that was about the die. Sorry about it. Yeah.
So how do you scale up across multiple cards? Like what connectivity do you have for that?
Right now we don't have CXL. We have PCIe 5. Yeah, and then we use software. We have software to participate in the model, and then we aggregate the result through the PCIe switch. Yeah.
And for inferencing very, very large models, inference large models, how would you break up the DLRM? Would you do a portion across different chips, or would you do the whole model at very, very low batch?
Yeah, for the model too big to fit into a single card, we participate into multiple card, and multiple card. Actually, I have my CTO here. If you are interested, we can talk offline here. Okay, his name is Joe over there.
Hi, this is James again. I have one more follow-up question. What kind of pricing range that you're looking at? Do you have anything?
Say
the pricing. The price?
The price?
Yeah.
Oh, the price has to be competitive. It's we care about performance per dollar per watts. Yeah, it has to be very, very competitive. Yeah.
Okay. All right.
Yeah, I'm sure I say that we are with very good support from Taiwan's ecosystem, including Wistron. Wistron is our lead investor, and then we work together with not just the silicon but also the system partner. Yeah. Okay.
Okay, thank you, Youn-Long, for presenting, and thank you to NEUCHIPS.
Thank you very much.